Welcome back, everybody. We are to chapter 4, module 4, and we're talking about probability. Buckle up. This is this largest chapter in the entire course. Each section is quite dense as well. So here we go, part 1. So the basic concepts of probability, and in probability and experiment, is any process with uncertain results that can be repeated. Now that's an important thing, is every experiment must be repeatable. If it can't be repeated, then in science, what we do is we just disregard it. It never happened. Something was wrong, the equipment was broken, we don't know, we can explore why, but unless it can be repeated, then we don't count it. In the short term, results are uncertain. In the long term, the proportion in which a certain outcome is observed can tell us quite accurately the probability of that outcome. And that brings us to the law of large numbers. Basically, what the law of large numbers says is the more you do the experiment over and over again, you're going to get more and more accurate of the proportion that you're looking for. So what I often do in my classes is I will flip a coin 10 times and write down heads or tails. Heads being a success, tails being a failure. And when I look at it, maybe there were 7 heads and 3 tails, but you and I all both know that there's a 50% chance that I'm going to get a heads and 50% chance that I'm going to get a tails. And so what I'll then do is have my students all flip it 10 times, and I write the results of how many heads or tails, and I find the average. And that's much closer to 50% than my 70% that say I got. So that's the idea of large numbers, is the more times that it can be done, the more accurate we're going to be able to come up with a proportion. And so let's do some definitions here. Sample space often called S, of a probability experiment is a collection of all possible outcomes. Now that's the important part. It's all of the possible outcomes. So let's say that we have a die. Let's see the color. The plural of die is dice. So really a 6-sided die. All of the outcomes are going to be a 1, a 2, a 3, a 4, a 5, or a 6. That's it. I'm never going to roll a 7. I'm never going to roll a 0. I'm never going to roll a -5. I'm never going to roll a pi. This is the entire sample space, all of it. Next up, we have an event. Is any collections of outcomes from a probability experiment. Events may consist of one outcome or more than one outcome. We often use E, F, and G to represent events when we do that. An unusual event is an event that has a low probability of occurring. And typically we arbitrarily kind of say less than 5%, but depending on what you're doing, you can certainly move that to wherever is appropriate for your particular experiment. And finally, a probability. Model lists the possible outcomes of a probability experiment and each outcome's probability. Rules of probability. P of E being at the event, right? We mentioned that before. P of E represents the probability that event E occurs. Now, I won't use E very much. I will actually write out P of rolling a 7 or whatever it is that we're trying to do. P of E is always between 0 and 1 inclusive. The word inclusive here means that it could be, the probability could be 0 or 1 as well. So we're including the boundaries. In an event, if an event is impossible, then the probability is 0. So for example, a human being without technology walking on water, the probability of that happening is 0. If the event is a certainty, then the probability is 1, which means 100%. When I let go of this pen, it is going to fall to the ground 100% of the time. Are not impossible or certainty when we're looking at experiments. We're actually trying to figure out what it is. So most probabilities are between 0 and 1, not the endpoints. So here's our first example. Interpret the statement. The probability that an individual walks to work is 0.03. This means that if we survey 100 people, individuals, we would expect about 3 to walk to work. And we can understand this. 3 out of 100 is not very probable, meaning if we were to randomly select an individual, and this was a true statement here, then it wouldn't surprise us if very few people were able to walk to work. We're now going to introduce something called a tree diagram. Using a tree diagram to describe the sample space and the fundamental counting rule. So we're getting to the fundamental counting rule here in just a moment. So here we go. If a basketball player shoots 3 free throws, describe the sample space of possible outcomes using S for a made free throw and an F for a missed free throw. S meaning yes, F meaning failure. And then what is the size of the sample space? Let's write this out. So we are going to have, let's use some color here. The first shot is going to be a success or it's going to be a failure. Those are the 2 options for the first shot. The second shot, we have a choice. It could be successful or we could have failed it. The third shot could have been successful or missed. And I'm going to go ahead and write these out. All successes, success, failure, success, failure, success, success, failure, 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 success, failure, success, failure, failure, success, and failure, meaning could have missed all 3. So what is the size of our sample space? It looks like we have 1, 2, 3, 4, 5, 6, 7, 8. So our sample space size in this case is 8. If a person rolls a 4-sided die and then flips a coin, describe the sample space using 1, 2, 3 for the die and H and T for the coin. So our first roll of the 4-sided die, we're going to get a 1, a 2, a 3, or a 4. And then when we flip the coin, we're going to get a heads or a tails. And if we write those out, and it looks like we have a total of 8 possible outcomes. So this is the entire sample space here using a tree diagram. So we have 3 methods for determining probability. We have the empirical method, the classical method, and subjective. Subjective method is a terrible method. That means that this is when someone says 90% of the people agree with me, and they have no basis for that 90%. They're just saying 90%. That's the subjective. So that's not a good way to do probability. A better way of doing probability. So we're going to use the empirical approach. We have the probability of event E. Relative frequency of E is going to be the frequency of E divided by the total number of trials in an experiment. And we can see this best if we do an example. What is the probability? So we have, in a survey of 1,100 female adults, it was determined that 341 volunteered at least once in the past year. Find the probability that a randomly selected female adult volunteered at least once in the past year. So the probability that these women volunteered is going to be the 341 out of the 1,100. Let's turn that into And by the way, our probabilities, we can leave them as fractions, we can turn them into decimals, or we can turn them into percents. Those are our three options. I'm gonna turn this into a decimal. 341 divided by 1100. So the probability of randomly selecting from 1,100 female adults that they volunteered at least once last year is 0.31 or 31%. And what I just said is the interpretation. Let's do another example. A survey of randomly selected high school students determined 288 played organized sports. What is the probability that a randomly selected high school student plays organized sports? That is going to be the 288 out of the 500. We'll turn that into a decimal. And then a percent. So 288 divided by 500. So here's our probability. If we convert that to a percent, that's going to be 57.6%. Now the classical method's about the same. And we are going to have for example 4, we're going to let the sample space S be 1, 2, 3, 4, 5, 6, 7. Each outcome equally likely. Compute the probability of the event given. So events E, F, G, and H. Answer it as an integer or a simplified fraction. So in this case, they're prescriptive. They're telling us how to do this. Let's start with part A. Probability of event E, which is defined here, an odd number. Numbers are there. There's 1, 2, 3, 4 odd numbers out of the 7. Part B, probability of event F. F being an even integer less than 6, even less than 6. So that's 4 and 2. So there's 2 of them out of the 7. See the probability of event G happening. G is a number less than 10. All of these numbers are less than 10. – 100% of the time, if we select any of these numbers, they're all going to be less than 10. Probability of event H, H defined as a multiple of 3 or an even number. A multiple of 3, that's 3 and 6, or even, that's 2, 4, 6. Now notice 6 is counted twice. So let's start with multiples of 3. There are 2 multiples of 3. There are even numbers. There's 1, 2, 3 even numbers. But I double counted the 6. That's going to give me 4 over 7. So I had to subtract off that extra one. That's going to become a here in just a moment. We'll talk more about that subtract in a second. Example 5, a pair of dice is rolled. We're assuming these are 6-sided dice. And I put a little chart here for you so you can see here are all the probabilities, all the possibilities, pardon me, of what you can roll when you roll 2 dice. And part A says, what's the probability? And by the way, there is 6 by 6 or 36 is going to be my denominator. Probability of a 7. How many 7s are there? Well, let's take a look. There's 6 and a 1. 1, 2, 3, 4, 5, 6. There's 6 chances of rolling a 7 out of 36. And they say a simplified fraction is how they want this written. So a 1 out of 6 chance that you'll roll a 7. Part B, snake eyes. If you are not familiar with dice, snake eyes means a 1 and a 1, meaning that's not good. And if we're playing a game called craps, when you roll snake eyes or a 2, 1 and 1, you automatically lose. So that's not good. But there's only one way to do that out of 36 chances. So fairly low probability. But just because something's a low probability doesn't mean that it can't randomly happen. It certainly could. All right. Let's keep going. Compute the probability of having exactly 2 boys in a 3-child family using the classical method, assuming that the boys and girls are equally likely. Without getting into what gender means and all that kind of stuff, we're just going to go by the sex of the children. And I'm going to actually write out all the possibilities. So we have boys and girl. And a 3-child family. So that means the next child is either going to be a boy or a girl. The 3rd child is either going to be a boy or a girl. And let's write these out. And then we have here. Boy. 3 girls. All right, and what they're asking is, what's the probability of having exactly 2 boys? Well, let's see what that means. That is not exactly 2 boys, that is 3 boys. So exactly 2 boys we have here. We have here. We have here. That's it. And out of these 8, there are 3 out of the 8. Let's turn that into a decimal. That's exactly equal to 0.375. So assuming everything's equal, that any child could be one or the other, there are 3 possibilities out of the 8 that you're going to get exactly 2 boys in a 3-child family. All right, let's talk. I mentioned this before. A subjective probability of an outcome is obtained based on personal judgment, which is always a terrible way to do statistics. You never want it to be personal or based on emotion or anything like that. You want it to be as objective as possible and not subjective. Complement rule. We're going to use complements a lot in here, and I don't mean telling somebody that they look nice. I mean opposites. So we have 2 notations here. We have, if we have event E, then its opposite is E bar, which I usually use the bar, or E to the C power. That shows up occasionally. And the whole idea is that event E, the probability of event E plus the probability of not event E should always equal 1. Always, always, always. And we can rearrange this so I could subtract off one or the other to the other side. And let's do this here. So we want to find P of complement E is 1 minus P of E. And we have P of E is 0.29. So let's go 1 minus 0.29. There it is. And let's talk a little bit more about this. Let's go back to the binary gender idea here, which I know there's definitely non-binary, but we're going to pretend like for our purposes right now that it is binary. So a boy or a girl. So if I'm in a classroom and we are labeling men and women, if 40% of my class is men, right away, we know that 60% are women. That's literally the 100% minus the 40%. That's all that we're doing here. And we're moving on. Go. Example 8, a bag of candy finds 4 flavors. 80 of them are lemon, 35 are grape, 25 are cherry, and 20 are blueberry. If a candy is chosen at random, what is the probability that it is not blueberry? So here's the not idea. So the probability of not blueberry is going to be 1 minus the probability of getting blueberry. First of all, I need to know how many candies there are. So that's going to be 80 plus 35 plus 25 plus 20. 160, it looks like. So it's going to be 1 minus. Now, how many blueberry are there? There's 20 out of the 6. I can reduce that and get a common denominator. So there's a 2 and 3 shot that if I randomly select this candy, it's not going to be blueberry. Ooh, that's 160. So 1 minus 2 over 16, 1 minus 1 over 8. There we go. 8 over 8 minus 1/8 is 7 over 8. That is a better number. And I can even get a decimal from that, 7 divided by 8. So there's an 87% chance, 87.5% chance that I'm not going to get a blueberry. Let's do another example. Kind of hammer that in. All right, let's get that up. The data represents a number of live multiple delivery births in a particular year for women aged 15 to 54 years old. And we can see that it's broken down. Let's see how many total there are. This is going to be the number in the sample space. And that's going to be 92 plus 515 plus 623 plus 2824 plus 1852 plus 373 plus 115. I'm getting 7,394 women. We're going to go through. Let's start with part A. Probability age 30 to 39. Now I want to point out 30 to 39 are both of these categories. This is going to be my denominator. So my numerator is going to be 30 to 39. So that's 2824 plus 1852 over 7394. So 2824 plus 1852 divided by 7394. About 0.6324. About 60, a little over 63% of these women are between the ages of 30 to 39. And we all know women that the 30 to 39 is a very common age for women to have children. And so that's not surprising that it's more than half is there. Part B. Mother is not 30 to 39 years old. So P of not 30 to 39. Now I'm going to use the complement rule here. And I'm going to take the complement of that. I'll show you a little trick with the calculator here. So I'm going to go 1 minus. Now, if I want the previous answer, if you can see above the negative button, it says answer. So I'm going to hit second answer. And what that does is that brings all those digits there and allows me to use that number. So we're getting here so about 36, 37% of the women are not between the ages of 30 to 39 that had delivered multiple births. Part C. The mother is less than 45 years old. Less than 45, that's all of those. I'm going to do this. It's going to be 1 minus the probability of bigger than or equal to 45 years old. That makes it much easier. So that's going to be 1 minus 115 over 7394. So using that complement rule, I like it. 1 minus 115 divided by 7394. Now, I want to point out that they're saying less than 45. So that's all those. You could add all of those up without the 115, or you can do the 1 minus. I think it's a little bit easier to use the complement rule in this case. But if you wanted to add up the 373, the 1852, and so on, all those divided by that, you would get that same number. Part D. Probability at least bigger than 20. Again, they're equal to 20. And I'm going to do that's 1 minus probability of less than 20. Less than 20 is the 92. So 1 minus 92 divided by 7394. That's even higher, 0.9876. Oh, and they asked for as a fraction. It doesn't matter. It's all the same. E. The mother is less than 20 or greater than 44. So P of less than 20 or greater than 44. So that one I'm just going to flat out do. Less than 20, I'm at 92. Older than 44, that's 115. And in fact, I will show you a trick for this last one on how to keep it as a fraction. 92 plus 115 divided by 7394. So here's 207 divided by 7394. So here's the decimal answer. But if I want to convert it to a fraction, here's what I do. I go to math, convert to a fraction. There it is. It even reduces it for you, which is really cool. And you could do the same with each of those as well. All right, so now we have a deck of cards. If you're not familiar with cards, I'm sad for you. Cards are a lot of fun. There's more uses than gambling with them. And the size of the sample space is 52. Now, for those of you that are not familiar with cards, there are a 1 through 10, the one we call an ace, through 10. And then on top of that, we have Jack, Queen, King. These are called the royal or the face cards. In England, they're called the royal cards. Here, they're called face cards in the US. And with these, that makes up a total of 13 cards in each each suit. Linked out there for a second. And to be clear, the club suits are black. The spades are also black. However, diamonds and hearts, they are red, typically in a standard deck of cards. So you have half of them are black, half of them are red. Some of them, a fourth of them are clubs, a fourth are diamonds, hearts, spades, and so on. And so we are going to, by the way, our denominator is going to be every time with this. Let's start with A. The probability of a red queen. Well, here are the reds, and that's going to be a total of 2 queens out of 52. And we want this as a fraction as well, so it's a 1 in 26 chance. And let's see what the decimal looks like there. What that means is that we have about a 3 to 4% chance of getting a red queen, so not so high. Part B, a face card. Well, let's see how many face cards there are. 1, 2, 3 times 4. There are a total of 12 face cards out of the 52. And that's going to reduce to a 3 over 13. And I can double check that by using the little trick I showed you with the math convert. Yep, 3 over 13, which is how they want the answer written. And the decimal approximation of that is the 0.231, we'll say. Meaning there's about a 23% chance that you're going to get a face card, which in some card games, that's not so bad. Part C, probability of a diamond. How many diamonds are there? There's 13. 1 through 10, 11, 12, 13. 13 out of the 52. That's a fourth, or 25%, 0.25. Part D is the probability of the 2 of clubs. Well, there's only one of those out of the 52. So a less than 2% chance of getting the 2 of clubs. That's a very specific value. E, probability of black. Well, like I said, half of them are black. So that means 26 out of the 52, which of course reduces to 1/2. And F, probability of green. In a standard deck of cards, there are no green cards. That's going to be 0 out of 52, which is 0. And that is the first of 4 sections of probability.